Hi everyone, welcome back to Dave's Math channel. This is my third video on group theory. Today I'm going to talk about another important class of groups called permutation groups. Here's an example of a permutation on this slide, but I'll get into that more later. So first I have to review what a group is again. I did this in the last two videos, might as well do it in this one too. So a group is just a set, which we call capital G in this case, together with a binary operator, which we're calling big circle or big dot, if you like. Dot, I'll just call it dot. So it's G comma dot. Like I said, G is a set and dot is a binary operator, and dot has to satisfy the three axioms given: associativity, identity. I'm not going to go through this in detail. You guys can read them. And inverse. And also sometimes people include closure as another group axiom, but we're assuming that that goes into the definition of our binary operator dot in this case, so we don't really need that one. But anyway, that's a definition of a group, and any set with a binary operator satisfying these three axioms is a group. And in particular, permutation, there's a certain type of group called a permutation group. And first, I have to define permutations. It's a pretty easy concept. So just imagine you have a set with three elements, A, B, C. The first three letters of the English alphabet. So how many ways can you rearrange those letters? Well, obviously six, right? And they write them all out here: A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, C, B, A. Those are all the permutations of A, B, C. We're just shifting things around. And I think you could see that in my cover slide here. You're mapping 1 to 3. It's basically just a bijection. It's a bijection of the elements of a finite set. That's all a permutation is. Um, so anyway, and they call it a rearrangement too. There's different names for it. But that's a permutation. And if you compose two permutations, so what you can do, actually, there's different representations of permutations. First, I should talk about that first. So there's a thing called the cyclic representation. It turns out that you can break up every permutation into a product of cycles. These are just things where one element goes to another element, and that element goes to a third element, and so on until you get back to the one you started with. In this case, these 2 and 5 are what are called fixed points. They don't get moved. So we can write that in two different in other ways as well. So 1 is going to 4, so we write 4 below 1. This is a sort of a matrix. It's not really the matrix representation, but we write as a 2 by or an n by 2 matrix, in this case 8 by 2. 8 rows, 2 columns. There's always 2 columns. So in the first, we always write the number that the thing that the thing on top gets mapped to after you shift things around. So 1 in this case is mapped to 4. 2, like I said, is a fixed point, so we write 2 below 2. Let's see, 3 gets mapped to 7. 4 gets mapped to 6. 5 gets mapped to 5. 5 is the other fixed point. 6 gets mapped to 8, 7 gets mapped to 1, and 8 gets mapped to 3. So that's another way you can write it. Or you can write in the way they show on the bottom. You don't have to start with 1, 2, 3, 4, 5, 6, 7, 8 in the top row. So there's other ways you can write this permutation down. Those are just different representations. And there's also something called the matrix representation of a permutation. So for this particular example, it's common to use the letter pi to represent a permutation. So here we have a permutation of 4. This is the numbers 1 through 4. 1 goes to 3, 2 goes to 2, 3 goes to 4, 4 goes to 1. We could also write that as a matrix. So, in this case, I guess we write that as C sub pi. So, here we go. 1 is going to 3. That means we have a 1. We have the number 1 in the first row, third column. We have the number 2 in the second row, second column. And you can check that if you just do ordinary multiplication of matrices, you get the same multiplication, which is really just composition. If you think of a permutation as a function or a map, then our multiplication of permutations is just composition. It means you're doing one permutation first, and then you're following it up by another permutation. Remember, you always multiply from right to left. You always compose functions from right to left. And if you do that, you'll get, it'll be isomorphic to the matrix representation. Um, and here's just an example. So suppose these are two permutations here. 1, 2, 3, 4. One goes to 2. Well, remember, we have to go from right to left. So our first permutation takes 1 to 2, 2 to 3, 3 to 1, and 4 to 4. Our second permutation takes 1 to 2, 2 to 4, 3 to 3, and 4 to 1. If you multiply those, you get a third permutation that takes 1 to 3, 2 to 4, 3 to 1, and 4 to 2. And you can check for yourself that if you do the matrix multiplication, you get the same thing. So anyway, that's composition of permutations, and it kind of proves that the permutations form a group. Anyway, so that's permutations. That's how they're group structured. But now there's another thing I have to talk about regarding permutations. That's even and odd permutations. It turns out you can divide every permutation of any finite group, any finite set, into what are called even and odd permutations. What does that mean? Well, it turns out that every permutation has can be represented as a product of two cycles. Two cycles are also called transpositions. They're just cycles of length 2. So, for instance, the permutation 1, 2, 3, 4, 5. This is a cyclic permutation that rotates everything 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 1. You can write that as the product of the transpositions 1, 5, 1, 4, 1, 3, 1, 2. You can check for yourself that that's true. And so it says four two cycles here, 4 transpositions. That's an even number. That means this is an even permutation. And there's other ways we can write it as a product of transpositions. For instance, the thing on the bottom here. This is a more complicated representation. 2, 1, 2, 5, 2, 4, 2, 3, 1, 4, 1, 4. This has length 6. It's still an even number. It turns out no matter how you write this as a product of transpositions, the number of transpositions may be different, but it's always going to be even. And there's other permutations called odd permutations where the number of transpositions is always odd. So those are even and odd permutations. And then we can define some special groups, which we call symmetric and alternating groups. These are just groups of permutations. So the symmetric group of n permutations, we write that as S sub n. I think I'm jumping the gun here a little bit, but if we had a set S, and it can be finite or infinite, we can define the set of all permutations of S as sim of S. It's just a symmetric group acting on the set S. Similarly, we can write alt S as the set of all even permutations of the elements of the set S. I guess for that case, S has to be finite. But then we can, the next thing we should note is that these groups, these sim S and alt S, they really, in terms of the group structure, they don't depend on the details of these sets S. They only depend on their cardinal number, the number of elements. So it turns out that if S is a set of order 3, say, and T is another set of order 3, then sim S and sim T are isomorphic. They're both isomorphic to this thing we call S sub 3, which we call the symmetric group on 3 letters. And a general S sub n is a symmetric group on n letters. These things grow very fast. It's pretty easy to check that the number of elements, the total number of permutations of any set of order n is equal to n factorial. I think that's pretty easy to see because there's n possible ways we can map the first element, but then there's another n minus 1 ways we can map the second element. Remember, we can't map it to the same thing as the first element, so it has to be something different. Then there's n minus 2 ways we can map the third element, and so on, all the way up to the last element that has just a unique map. So that makes a total of n factorial. N times n minus 1 times n minus 2, all the way down to 1. That's n factorial. That's pretty easy to see. That there's n factorial permutations of any set of order n. And since half of the permutations are even and the other half are odd. That's another fact I didn't mention, but it's true. As long as n is greater or equal to 2. And that means that the order of an, that's just the isomorphism class of all alternating groups of order, then that's n factorial over 2. That's half of all the permutations. That's going to be n factorial over 2. And these factorials grow very fast. I mean, you don't have to get to very large values of n before these groups start getting really, really big. By the time you're up to n equals 10, there's already, 3,628,800 total permutations. And there's half as many of that, 1,814,400 even permutations. So these are the size of S10 and A10. They're huge groups, and they get big really fast. And yeah, here's an example, S3. These are just all the elements of S3. We can call them alpha and beta. Turns out alpha and beta generate this group. Yeah, E is just the identity. That's everything that fixes every element. Alpha, that's the cycle 1, 2, 3, just the thing that maps 1 to 2, 2 to 3, and 3 to 1. Beta is a thing that transposes 2 and 3 and fixes 1. So 1 goes to 1, 2 goes to 3, 3 goes to 2. And it turns out alpha and beta generate S3. So it has two generators. But it's what's called a non-abelian group. That's just a fancy name for a group that doesn't commute. It's not commutative. So, for instance, alpha beta is not the same as beta alpha. Beta alpha turns out to be alpha squared beta. So this is an example of a non-abelian group. And it turns out that Sn is non-abelian for n greater than equal to 3. I think An is as well. So, and I think non-abelian groups in general are a lot more interesting than abelian groups. But anyway, and here's the Cayley table of S. This is a Cayley table is just another name for group multiplication table. This shows you how you can multiply all permutations of the numbers 1, 2, and 3. And it is a non-abelian group. Yeah, as you can see from the Cayley table, if you multiply 1, 2 by 2, 3, that gives you 1, 2, 3. If you multiply 2, 3 by 1, 2, you get 1, 3, 2. So it's not abelian. And there's also something called a Cayley graph. I think this is kind of a neat picture. So S4 already has 24 elements, and they write them all out on this picture. You can write, and these are just the things that 1, 2, 3, 4 gets permuted to. And you can, the arrows just kind of represent the elements of the group. Remember, element of a group is a permutation in this case. So if you look at one of these arrows, like 2, 4, 3, 1 goes to 1, 2, 4, 3. That's one of these red arrows on the left. That's a permutation. And you can compose two permutations just by joining up the arrows. So this is a graph. And for instance, if you follow a graph like yeah, so we have 2, 4, 1, 3 goes to 4, 1, 2, 3. That's one permutation. Then we have another one that takes 4, 1, 2, 3 to 1, 2, 4, 3. Turns out that that is equal to the permutation that takes 2, 4, 1, 3 to 1, 2, 4, 3. So there's different ways you can represent these permutations. This is the Cayley graph. Just thought I'd show you that. Anyway, I think that's all I have to say today about permutation groups. They're very important. You'll see them in many, many contexts in group theory. As a matter of fact, it turns out that every finite group is isomorphic to a permutation group. That's a pretty easy thing to prove. I think I forget the name of that theorem, but it's an important theorem in group theory. So permutation groups are very important. Anyway, that concludes my video. So thank you for watching. Long live math, and I'll see you guys next time. Bye.